Here's a quadratic equation, and we're going to add negative 35 to both sides so that the right side of the equation is equal to 0. Then we're going to look it over and see if it can be factored, but it can't. So now we're going to add 15 to both sides so that we have x squared plus 6x on one side and 15 on the other. And then I'm going to add the number that I need to add so that the x squared plus 6x plus my new number is a perfect trinomial square, and that number is 9. But of course, if I add it to the left side to make that a trinomial square, I need to add that 9 to the right side as well. Then I factor the left side. I get x plus 3, the quantity squared, and of course 24 plus 9 is 33. I take the square root of both sides, and then I add negative 3 to both sides, and I get my solution. There's actually two solutions, negative 3 plus or minus root 33. Now you may ask, how did I know to add 9 to both sides? Well, what that 9 is half of the coefficient of x, which is in this case 6. I divide it in 2 and then square it. So it's a bit complicated. But after I get the x squared plus 6x, I look at the 6, I chop it in half, and I square it. And 6 divided by 2 is 3, and 3 squared is 9. And that's how I knew that I needed to add 9 to both sides. Let's look at another. We set one side equal to 0. It can't be factored. So then we add 22 to both sides. So it's in the same form it was in our last equation. We have x squared plus 12x this time, equaling 22. I'm going to add something to both sides that I hope will make the left side a perfect trinomial square, and it does. So on the right side we added 36, and that made 58. And on the left side we had a trinomial that we factored as the quantity x plus 6 squared. Take the square root of both sides, and then add negative 6 to both sides. And there's our solution, negative 6 plus or minus root 58. And once again, see if you can remember how I picked 36. I looked at that 12 up there in line 3. I cut it in half, which is 6, and I squared that, and 6 squared is 36. And then I added that to both sides. Here's another example. Only this example, there's a 3 attached to the x squared term, so that's going to complicate things a bit. But before I do anything about that 3, I'm going to add 4 to both sides so that I get 3x squared plus 12x is equal to 22. Now I'm going to divide everything by 3, and that'll give me x squared plus 4x equals 22 thirds. And now, of course, I'm ready to look at that 4, chop it in half, and square the result. Well, 4 over 2 is 2, and 2 squared is 4, so I'm going to add 4 to both sides. Well, the left side, x squared plus 4x plus 4, is, of course, a perfect trinomial square. And the right side, when you add 22 thirds to 4, since a 4 is equal to 12 thirds, 22 thirds plus 12 thirds is 34 thirds. And now we take the square root of both sides, and we get that x plus 2 is equal to positive or negative root 34 thirds. And then we need another page to finish this off. We're going to add negative 2 to both sides. And we're going to leave this alone, but it's actually not in simplest radical form because we don't like to have square roots of denominators. But we'll talk more about simplest radical form in subsequent lessons. So for now, this is the exact answer, and we solved this quadratic equation by a process known as completing the square. And here's the generic form for a quadratic equation. You set one side to be 0, and if you're left with ax squared plus bx plus c is equal to that 0, then this is the type of quadratic equation that can be solved by completing the square. And here are the steps. You add the opposite of c to both sides. Then you divide both sides by a. And then here's the tricky part. You add b over 2a squared to both sides. And we'll get to why that is in our next example. And then you factor the left side, which of course should be a perfect trinomial square if you've done everything correctly. Then you take the square roots of both sides, and you perform transformations as necessary to solve for x. And now let's work through one more while we look at the rules while we do the steps. So the first thing we're going to do is we're going to start with an equation in the form ax squared plus bx plus c is equal to 0. And then we find c, which is negative 8. So we add the opposite of c to both sides, which is positive 8, giving us 5x squared plus 9x is equal to 8. We divide both sides by a, which in this case is 5. And then we simplify those results, and that gives us x squared plus 9/5 x is equal to 8/5. So the new coefficient of x is 9/5. And we want to divide 9/5 by 2 and then square the result and add that to both sides. And as I've stated before, dividing the 9/5 by 2 and squaring it is the same as b over 2a squared. And let's take a little break and show the arithmetic as to why it becomes b over 2a. Well, let's look at the original generic form of a quadratic equation. We add the opposite of c to both sides. We divide both sides by a. And we get x squared plus b over a times x is equal to the opposite of c divided by a. And so now we're looking at b over a. And again, we want to take that b over a, which is the new coefficient of x, divide it by 2. But dividing by 2 is the same as multiplying by 1/2. So if you remember your rules for the multiplication of fractions, b times 1 is b, and a times 2, using the commutative property, is 2a. So there's where the b over 2a comes from. And applying it to our current example, our b over a is 9/5. So we're doing 9/5 divided by 2, which is the same as 9/5 times 1/2. 9 times 1 is 9, and 5 times 2 is 10. So in this case, it's 9/10. So 9/5 divided in half is 9/10. Then we're going to square that and add it to both sides. So we had 9/5 divided by 2. We now know that it's 9/10. When we square that, we get 81 over 100. So that's what we're adding to both sides. And of course, this becomes a little problematic because all the factoring we've done so far has involved integer coefficients. And here we're trying to factor something involving fractions. But it's a special case because of the perfect trinomial square. We know that 81 is a perfect square and so is 100. So when we factor the trinomial on the left side, we're going to get x plus 9/10, the quantity squared. And the arithmetic for the right side is that 8/5 plus 81 100ths is 241 100ths. I've run out of room, so I'm going to recopy the last line from the previous slide. And now I'm going to take the square root of both sides, and that gives me this. And then I'm going to do two things. I'm going to add negative 9/10 to both sides, which is a necessary transformation. And it turns out that in the square root of 241 over 100, since the 100 is a perfect square, I'm allowed to take the square root of that, which is 10. 241 is not a perfect square, so I'm going to leave it alone. And I get the expression shown here, but since they both have the same denominator of 10, I hope you all remember that we're allowed to write it as the two numerators over the common denominator. And that's the best way to express this solution. The quantity negative 9 plus or minus root 241 over 10. And we'll go over the rules one more time for solving a quadratic equation by completing the square. First, make sure your equation is in the form ax squared plus bx plus c is equal to 0. And if it is, you can add the opposite of c to both sides. Then you should divide both sides by a. Then you should add b divided by the product of 2 and a, all of that squared, to both sides. Then factor the left side, take the square roots of both sides, and perform transformations as necessary to solve for x. By the way, completing the square isn't something you're going to do a lot of in the future, but it's important to at least see it once or twice because it helps have a good understanding of something that is very important in an algebra course, and that's our next lesson, the quadratic formula.